Good afternoon, dear students. Hope that you are doing well and you enjoyed your weekends. So let's start the class for today. And the good news for you is today is the last class, and you will just then do your presentation on Wednesday. On Thursday, you will have final exam, which you are going to do it. I will just send the paper in Google Drive, and then you can do it like on the time from like 12:30 to 3:30 Afghanistan time, and then you can send me your answers personally. So if you don't have any question, let me share my screen. Can you see my screen?
Yes, teacher.
That's perfect. Just a second. Uh, we will try to cover up today neural networks and deep learning. We will just try to work with some basics of and to understand some basic concepts in neural network and deep learning, because nowadays it's all about these concepts in computer science. Well, you are discussing about machine learning, but apart from machine learning, that those are traditional models. Now they are trying to build on top of machine learning. Like there are, so how do you classify images? Like images, videos, voice, all of them. Now they are working on these new concepts like using LLM, large language model, or LNP, natural language processing. So these all are new concepts that are coming to computer science, and let's see how it works, and let's see how we can do it today in the class. Just a second, let me see. Okay, okay, your classmate is saying, okay. Uh, Let me go. Okay. So learning outcome for today's class is explain the basic structure and function of a neural network, including neurons, layers, and activation function, differentiate between shallow and deep neural network architectures, and describe their practical applications, apply activation functions, sigmoid, ReLU, tangent, hyperbolic, softmax, and explain their role in introducing nonlinearity. Also illustrate the forward path of simple neural network through step-by-step computation of weighted sums, biases, addition, and activations. Also identify the main components of CNN, convolutional neural network, which stands for CNN. What is convolution, activation, pooling, fully connected, and outcome layers, and describe their purpose in feature extraction and classification. Also construct basic network architecture for binary and multiclass classification tasks. So before we dive into this class, let me ask you some questions so that are you on board with me or not? Yeah. Okay. So would you trust a computer to choose your clothes? And are you interested or scared about AI? Why? Yes, Majima, please go on.
Thank you, teacher, for giving this opportunity. About the first question, would you trust a computer to choose your clothes? I think in this question, absolutely not. I am choosing a computer for choosing my clothes because the computer don't know what's our feeling when I'm using the clothes, and also how to choose the colors of these clothes, and also how is my personality, and also how is the culture of the area that I'm living in there. Just I can
Mhm.
use this one as a helper, but not as a decider for me. And regarding the second question, are you excited or scared about AI? Why? Absolutely, I can say that both is okay. Sometimes I'm excited about using the AI because it gives me some more information and also clarification, especially when I'm applying for jobs. It will help me to know how is the process for having the questions about maybe interviews and also written tests. It would help me about this one, and also it would make some creativity on myself because I can find many information about this one. But absolutely, I'm not scared about this one. Just I have a little cautious because sometimes the AI should be misused by someone, and also there is maybe some powerful people use these tools. Just we knew that in itself, so it owns AI is not good and also not bad. Just this depends on the using of these tools that we are using in a good way and also are using in a bad way. Just if we imagine a knife, it can cook for us. This is the usefulness of these tools, but sometimes it can hurt us as well. This AI is also the same as the example of a knife. This is my idea about this one, teacher. Thank you.
Okay, thank you, Majiba. Anyone else? Would you trust a computer to choose your clothes? Regarding your question now, Majiba, before you can just keep in mind, let's go to our fellow here, maybe ChatGPT. You said about Afghanistan. So let's see how it works. If I say I am a rural girl in Afghanistan, please uh, give. Let's see what will be the Majiba.
Yes, and here I think just we are saying about the matching colors. We can take this help from computer. Just because of this, I say that is also as a helper because we can also know some maybe cultural, but depends on not just in here because we have some culture sensitivity as well.
Yeah, you are
The,
right.
the
When it comes to
internet, I think,
Afghanistan, you are
cannot
right.
be do all of this.
So what do you think now regarding these pictures? Okay, anyhow, it's your opinion. I respect your opinion. So nowadays, I just want to show you that nowadays many things are uh, decided or can be you can take help as Majuba said in her answer that can take help from or assist guidance from computer to choose the better or what is good and what is bad. Anyone else?
Sorry, teacher, can I say something?
Yes, Atfa, go on, please.
How much can I trust on computer to say to search or to ask something from AI or computer? It depends on that something that I'm searching. I think about our cultures, about our situation. I think we don't need to get any information because we are adults, we are young, and we know as much as we know we want. And our mother, our family can give more information, suitable information that we need. So we don't need to search anything from these digital tools. But sometimes that as we are employees, as we are a trainer, as a teacher, we need to search something from computer, and sometimes I want to join in a party, in a formal or official party, and I think it doesn't matter to search anything about my clothing, my speech, that I want to say something in their party. But so totally, I think it depends on those things that we are searching and our situation. And for the scary of I think AI is still now it's free, and it is a digital tool that they are its company is also gathering some data from their customer, and we have to careful about our searching, about our name, our private data. uh, it it means we don't have to be scared, but we have to be careful about anything that we are write in the box of AI, or some photos, personal and realities that it is just from ourselves, and it should be private with ourselves. It shouldn't. It doesn't need to share with anyone and with AI. Thank you,
Good.
teacher.
Thank you, Atifa. Thank you. You are good. You are correct. Okay. I think there was Mariam, but at last moment she just okay. Okay, now let's go into this course. What are neural networks? Neural networks are a core concept in modern artificial intelligence inspired by how the human brain works. A neural network is a computational model made up of layers of interconnected neurons or nodes that can learn patterns from data. So it's just like a human brain. When you see something, so you start to learn from this one. And also it was inspired by human brain. Each neuron process input applies a mathematical function and passes its output to the next layer. So you can see we have image recognition used in apps to detect faces, recognize objects, and unlock your phone with facial ID. So you can see all of them in your daily life. Also, language translation, powering a service like Google Translate to translate between languages in real time. Medical diagnosis, assisting doctors in detecting diseases such as cancer from medical images or predicting patient outcomes. So why they matter? The first one is learn complex patterns. Neural networks can discover hidden relationship in data without being explicitly programmed. Now, what does a hidden relationship means? We can go and in the next slide, we can see what does it mean really. Because you don't know some patterns, but it will learn by itself. The computer will learn, and you don't need to explicitly tell the computer that these are my hidden or my secret layers that you should touch them or no. They will find out and they will try to manipulate with those data. So high accuracy, they often outperform traditional algorithms in areas like image, text, and speech recognition. Scalability, as more data and computing power become available, neural networks become even more powerful. Foundation to deep learning, neural networks are the building blocks of deep learning, the technology behind many advanced applications today. So brief history of AI and neural networks. Like some people, they think that deep learning or new AI started to be in the market after once we were saying about this ChatGPT, DeepSeek. After these people got to know about AI more frequently. But that real thing is that if you go to the first era is perceptron era, it is 1958. So in 1958, people were after AI and neural networks. So the first neural network model, the perceptron, was invented in 1958 by Frank Roosevelt. It could learn simple patterns and inspired the idea that machine could learn from data. But perceptrons could not handle complex problems like language or vision, which led to merely uncertainty. So if you say it's from like a decade or so, no, it was just first time it was from 1958. But after that one, because there was some uncertainty, that's called AI winter, which is from 1970s to 1990s. So limited computing power and weak result caused a decline in funding and interest in AI. Many research projects were paused and or abandoned. Because of this uncertainty, then people start to neglect or just declare there was no funding for them and they lost their interest in AI. Then after that one, from 2000s up to present, then deep learning era with more data and powerful GPUs, graphical processing units, multi-layer neural networks became practical again. Then after this one, and the key breakthrough is in 2012, a neural network won the ImageNet large-scale visual recognition challenge, drastically reducing error in this one. So we can see this one ImageNet in, if we go to Google, if I close this one, ImageNet 2012 winner. So this module, this algorithm was that ImageNet. So you can say ImageNet. This is a very big library. You can find this one. So ImageNet large scale visualized recognition challenge 2012. So this one was the first time that some developers used this module, this deep learning, and this one of like the award. So this now you can see the validation and test data for the competition will consist of 150,000 photos. So there is like this much amount of photographs inside this data. So they just tried to use ImageNet, and then they wanted this ILSVRC 2012. You can see now this one was classification task, classification with localization. These all modules they applied and they won, and these were the organizers that they won this competition. So now for now it was this much. It was this much, but now it has been more than this much. So now you can see that the amount of images now they are training on is like this amount. So it is just nearly more than what can say 14 million. So more than 40 million data like images are trained on this now. So if you go to download, you can just see all of them challenges Kaggle. So in Kaggle, you can might find the subset of this ImageNet. So there could be. So it was here. You can see. So this is contents of this much. So this is the subset that they were putting in for the competition in this period of time from January 3rd to 2018 to 27th of March 2020. So this one was some images. So there were some competition. So this is the competition it was. So you can see here how they were. So after this ImageNet, people start to use deep learning more and more. And then in 2017, transformer models were introduced, revolutionizing natural language processing, MP, and enabling tools like ChatGPT. So then it started to come up with ChatGPT, DeepSeek, Gemini, and other cloud, and many more. Sony. So each company now they have their own. They are trying to make their own AI tools for their customers. So deep learning is a subfield of machine learning that uses multi-layered artificial neural network to automatically learn patterns and representations from large amounts of data. It mimics how the human brain processes information, learning features directly from raw input. Example, images, video, and text. Deep learning models improve as more data and computations are provided. So the feature is learns features automatically. Just you need some amount of code and it will start to learn it automatically. Then use multiple hidden layers in neural networks, excels in handling complex high dimensional images like speech, text, or something. Also, you can see powers many modern AI tools, chatbots, medical diagnosis, and autonomous vehicles. So this is application of deep learning. You can see image and videos, object detection, image segmentation, and medical images and video analysis. Self-driving cars, you can say tumor detection, facial recognition, and surveillance systems. In text and speech, you know that sentiment analysis, chatbots, translation, speech recognition. So you can see the examples in virtual assistant like Google that you're using Google Translation, real-time translators, text analysis tools, healthcare and climate predictive diagnosis, patient monitoring, environmental modeling, and also you can say disease prediction, air quality monitoring, and there are plenty of these ones. And also business and industry, fraud detection, recommendation system, which Netflix and is using most frequently when you see one movie, so it recommends you for the other one. So you can see they are using this recommendation system for businesses, for their business, predictive maintenance logistics. So bank fraud alerts if there is any fraud or there is any money that is amount is a lot or there is some problem. So it will just try to detect that fraud. And also product recommendation, factory monitoring, and all of them are now done with the use of deep learning. So one of the examples that I can show you, it was my thesis about these. So we were discussing. So this is the article which was in IEEE Explorer published. So it was a model of for Leishman's disease classification based on machine learning and deep learning algorithms. So you can see here that with the use of machine learning and deep learning, so you could classify Leishman's disease. What is Leishman's? Leishman's is called in Farsi Saldana. So this is Leishman's. If I copy paste this one, so you can see.
Teacher, we call Leishmania as well.
Yes, Leishmania, and we can say it's Saldana. So you can see that this is the fly bee. So this is the person, or not the person, it's the animal or insects that bite, and it makes you like this. You can see this one. So this one was my thesis that I was exploring machine learning and deep learning model algorithms. So in here you can see that the models that I was discussing with you was one of them is like simple machine learning convolutional neural network that we are discussing today, and transfer learning models, which I said you that on top of now this deep learning they are making some transfer learning modules. If you go deep inside machine learning and deep learning, you can find out this what's transfer learning. So they have already made some algorithms that you can just take those ones, or you can just take some layers from this one and train your model and see uh, the result of your model. So you can, if I can open this one, you can see. So it's a pre-trained machine learning model. So it's already trained. So that's why they are called transfer learning. So designed by a model architecture that allows specific components to be reused. So they are already pre-trained and you reuse, adapt, and combine for new and related tasks. So for your need, you will just reuse or you will combine some features and then train your model based on this one. So you can see that the ones that random forest, SQGOS, decision tree, naive Bayes, nearest neighbor that we were discussing how we were doing, so and support vector machine. So now there are plenty of algorithms, so you will just see all of them together and then you will find the best result for yourself. So with the given data, support vector machine performs better than the other machine learning algorithms. However, in convolutional neural network model, the images are directly fed to the CNN algorithm cylinder. So you can see now from these much models, like only for traditional machine learning, which one was very good? This one, support vector machine, which is SVM. You can find out that only one of these or the best one you will just find for yourself, and you can just see how it works. So for example, then this one was the paper. Then you can see that this is the website. Somehow it's very basic, or you can say not much. So we just to show that how it works and what was the result. So you can and show it, and you can deploy. So you can find out this one AI predict.netlify.app. you can find all of them here. So there is some this case you can find out in the navbar. There is home. So this is like someone was telling about HTML and CSS, so it's just basic of those one. So there is home, Lakshmana inspiration, add user, contact us, and log out. So you can find all of them here. And if you log out, then you need to have your ID and also password, so that you should enter to this and use this feature. If, for example, I log out this one, so I will not be able to use this feature. So you can see this is simple page. But if you just click on this portion, now you can find out. So in Lakshmana's prediction, we can find out this page here. It's just like small, you can see it. Now we can have your patient, the full name, age, what's the gender and date of birth. Then you can also upload your hospital or clinic logo. It's optional, but you can do it. For example, if it is your hospital or clinic, so you can just browse your and just put some pictures of the here. Then you can check your model. See, you can see CNN, transfer learning model, and multi-challenge model. So in here, you can see those all models that how it works. Now, for example, if I browse this image and this is the microscopic image for my for this disease, which I got from here from internet. Now, if I upload this one, now I can say that name is, for example, Ali. The age might be 22. Now, gender is male or female is male. So, and then you can find out date of birth. So, the date of birth is like, for example, 19 something. And then so I will use CNN model. So I will say that optional, it's optional that what do you think, what is it? So when I can see, okay, maybe it's positive. So I will just enter. So this is, but if I do it, it's up to me. Otherwise, it's optional. This portion is optional, whether you're going to predict or no. But in here, this is how the computer will program. We'll see. So it's here, prediction is positive. It means that this is Lakshmana's image, and its confidence is like near to 100. So it's very a lot, and actual is 1. So it means it is positive. So you can see this is the image of name of the image, and this is the prediction and confidence and actual. So you can see the graph. So if I go and then download this download button, so now if I download now if I open, now you can see here, for example, this is how it will come as a report for you. So this is the University of Central Asia. This is, it could be your hospital name here. So the phone number, email address, like clinic at U Central Asia. Then the report is, so patient name is Ali, age is this much, gender is this, and this is, and then this was the image name, the image that from them, and this is positive and how much. So you can see, and if you scan this one, it will show you the name and date of birth. So it means that, so that if you scan, anyone scan this person, because if you scan, so you can understand that this person is really, this belongs to this, for more, make it more secure. And then there is only need for doctor's signature, and this is, and it will show you when it was generated even. So it was generated at this time, so it's 12 or this one 8:32. So this is how you can do it while playing with deep learning and machine learning. So this is a small example of how you can do it. And what things, if I, for example, now log out, so you can see now if I log out, so there is no this one. If I log in, then there will be, but this is how it works. So I hope you understood the importance or applications of deep learning, that how you can do deep learning.
Sorry, teacher.
Yes, Atifa, please.
Sorry, teacher. Is it a reality?
Yeah.
This, how can we? Is it valuable? Yeah. I mean, can I use it for any documentary, or present this document for my healthy situation, to show I am healthy and I don't have any Leishmania disease?
So this
Is
is
it
only
valuable?
for, this is only, yeah, it's available, Atifa, but the thing is that this is only for Leishmania's prediction. So if you will take an image of your microscopic, so you can see here, there should be recon here.
For any
So
other disease, teacher,
so you have
what
to
should I
do,
do?
so for all the diseases, it cannot be. So it means that I was working on one disease. Atifa. So when you are working as your hypothesis or your research question, so you are doing it for one disease, not for multi one. If you are making for multivariate or something, so that's up to something else. You can put many images together and you can train differently, and then you can take out your inputs and then your model. When you are save your models, you can put it. So in there, when if I just wanna do it, so as you said, I can put another model also. For example, I will train for maybe for another disease. So I will just put instead of Leishmaniasis, I can say that there could be. This is only Leishmaniasis prediction only. And this paper is based on how it was done for Leishmaniasis. So you can see Leishmaniasis is caused by Leishmania presence and present consider. So this work see, this is the sentence. This work uses an approach for identifying Leishmaniasis images as positive or negative. So this is only for, and this one was for conference education. So it was published in Malaysia. You can see this is the published by. So it is in IEEE. You can find out this paper here. International Conference of Computer Application and Industries. So you can find it here. Somewhere here it is. This one was, there are plenty of papers, so this is part of this paper. So when you are doing, so you Atifa or everyone, so you will just take an question, research question, not for all. So you might do it for simple things first, then you can. Now, for example, this person is doing prediction of Barajan planet disease supporting using support vector machine. And so now if you just see, now this is only this disease. I say, if you read, this one is only for one disease. Or something like I have a hybrid of see, this is for only chronic kidney disease. So there is a hybrid deep learning approach for chronic kidney disease. Detecting using convolutional neural and support vector machine. So they have used CNN and support SVM to detect chronic kidney disease. So now this is only based on kidney disease. Now we can see this is in order to improve patient outcomes and reduce medical costs. Chronic kidney disease, a global health concerns, requires early detection. So for early detection is clinical biomarkers and subjective, the time consuming. You can read all of them. So you can see this is all the papers that you are doing is only one for one question, not for all. You will not answer for everything. Did I answer your question, Atfa?
Yes, teacher, thank you.
Yeah. Yes, Fatima, go on.
Thank you, teacher, for giving the chance. I have a question because I couldn't get exactly the point. Is that is that picture will generate by AI diagnosis based on our research details or research question, something else that you said? And is that right, or we will put the image and put the detail and the AI diagnosis will generate a picture.
So you will take the microscopic image of a patient and you will just put give it to the in here. You will just give it here and it will generate it whether is it Leishmania or no.
Got it.
So what is the need that if everything is done by, so you are just trying to make the life of people easier. For example, this one kidney disease. So kidney disease requires early detection. If someone has any problem, like for example, this author is like working on this problem, like kidney. So now they have shown that how much is 96.8. You can see here 18. A model achieved a notable accuracy of 96.18. High dimensional features representation are effectively okay. From CNN model convolution, if you put an image of a disease, of a patient of kidney disease, if he has kidney or no, then it will understand 96% of the time. It will give you a result. Accuracy is like this much. Did I answer your question, Fatima?
Yes, teacher. At the end of that, in the image which was generated by AI, we will put the exact resource. The picture is generated by these
No, no,
model
no.
of
The
AI
picture is
or not?
I took the picture from here because I found out one picture. So this picture was from here. This it was somewhere here. This was the picture that I took.
Got it, teacher. So we will mention the source of the picture from where? From there that we got the picture?
No, you will have your data set. You will have your data set, you will have data, you will train your model, and then you will give your result findings. Then the people, if someone comes, then they can give any image of them. It could be like any image. It could be any image. You will just put it, and the system should understand because you have trained your data. Now it's about your testing.
Got it. Okay.
So this is the application of deep learning. Hopefully that you have gained some idea. So now how it works. Now this is the very good thing. Now it's here basic. So you have an input. For example, you have to label cat and dog. So you will have some images, labeled images as your input. So this is where the data enters the network. So you will have some images, you will give them. And there is like, for example, you can see here cat and dog. Hidden layer, these layers process the information through many interconnected neurons. Now these images is converted into hidden layers. You are not going to give it explicitly to this computer or something. It will understand and it will form a hidden layer. We can see this one. So each layer, each neuron applies an weight, importance, adds biases, and presents the results through an attention function, a mathematical decision maker. So each layer, each of these layers will have a weight, like Wasandara, a bias. So there might be some ups and downs. Might be plus something or minus something because you can see that it could be a bias. And the causes a result through activation function, and there are some activation functions that you will it's met, for example sigmoid or linear or tangent hyperbolic. These are ReLU functions. So there are some functions, just you will just add those functions inside. It's math and it will understand everything. So the network learns by just adjusting these weights and biases during training. So it will just adjust you. It will be some kind like trial and error. So it will just give more, sometimes maybe it will give some more weight, but it's the result is bad, so it will just adjust it less or something. So it will just adjust is based on the network itself. Then you will have your output. You can see, is it a dog or see? If you put an image like this, so it will understand it's a cat. Oh, cat for it. Like for example, how it works, like we can see it here through, there is a TensorFlow playground. You can see here, for example, yeah, you can have this one, maybe another one with images. Let me give them images. If I can show you with images, it would be very good. Okay, no problem. We can use it from here. So you can see here, so there is some data. So you will have some hidden layers, for example, and here there are 4 neural networks. There is some hidden, so you can increase the hidden layer and you can see the accuracy. So if there is like test is this much, if I make it, so if it's 3, so the test loss is less, is more 0.5. But if I make more layers, so it will understand more. So it means that it's increasing. So it will be adjust by itself. So you can see this one. To some point, if you have more layers, it means that there is no any. But if I have less, so it will be changed. The training loss and everything will be changed. If I don't have, so it's all. So it's all that how you are going to play with this system. So you can have your accuracy, like I said, that it should be 70% of my training data. So everything you can see. And now if I see, so this is the test loss and everything. So this is how it works. But how we do it in real life, we can see it in an example. Do you have any questions so far from here?
Not sure.
Others?
No,
sir.
Okay, I think it's just simple English now, but how it works now we can see here. So this is how main components weighted inputs. So for example, this is feature 1, feature 2, feature 1. So feature 1 is xi and there is a weight. So, and there is x2, there is a weight. So these are all weight. So you can have summation of this one. So you will just add all of them and its biases. So each input xi is multiple by the weight wi. So if I show you here, this could be 1, 2, this could be like one feature, this could be second, this is third. Now I can add this one also, this one also, this one also. So it is now going to be the features. So you can see all the features. So which properties do you need to fit in? So if you need to fit 3 features, so I'll just disconnect this one, this. So this could be 3 features. So it will have its own, like you can see weight. You can see weight is 0.15. This has its own minus 0.48. This could be minus 0.05. So each feature has its own weight. So you can see this one is here, another weight. So this is the weight for this feature. So the same goes here, and then you will add this one, and there might be some bias. There should be some ups and downs because it will not be 100%. You are not sure, so you have some to add some biases. So this is, you have this feature. So this is the weight is 0.056. You can see each feature has a weight. So each expo is multiplied by weight. So you can see this is W1, W2, W3, W4. Weight controls the importance of that output. So it will see that how much impact this feature has on this one. If it is like high, so it means that it has more like relation. For example, in here you can see this one is 0.39. So it means that the importance is like 0.34. And here it's minus 0.014. So it means it's less. It's very less. If you have, it's also less. But this is plus because we have more blue, like here. You can see these blues. And so all the features are here. If you go for this one, maybe in here now the weight is changed. So it's 0.28. If I have this one, it will be again 0.08. So this feature has this much importance for this data set. So you can see all of you but for this one it is 0.6. So each data set has its own weight, its own importance. Each feature has its own. So if I regenerate, so you can see all of them here. Now if I go here, and as I said to you, so you will just pick all of them. So it's W1, X1, so feature 1 and its weight, feature 2 and its weight. So all, and it will be summation of Wi, Xi. And then is a bias. A bias B is added to the weight sum. It helps shift the output of the new, making the model more flexible. So you'll just have some extra bias or some a number or something so that it should give you, it should be more flexible for you. This is how. And then after this one, you have when you are here, this is summation. Now then you will give the result of this one to your activation function. So it could be a sigmoid, it could be ReLU, it could be tangent hyperbolic. It's up to you which functions you are going to use. So the activation function decides whether and how strong the neuron should fire, produce an output. It introduces nonlinearity, allows the network to learn complex patterns. After adding these one, after calculation of these, then you will give it to your activation function. So it is, the formulas are all given to you. For example, for sigmoid, so this is the formula. So 1 divided by 1 plus e raised to the power minus x. A sigmoid function is a mathematical function having a vector s. It's just like s. You can see here, it is starting from 0 to 1. It's bounded into this region. So often shows a return value in a range of 0 to 1. So you will have a value from 0 to 1, always it will be. So it's always positive. It should be positive because it's from 0 to 1, you can see. And bounded, it's from this region, and it's strictly increasing. So it's strictly increasing when it comes. If it is here, it will it's increasing function. So let's see an example. Now, for example, you have here, this is your example. You have like feature 1. Feature 1 is 1, feature 2, and feature 3. So you have like here, you can see, oh, this is no, sorry. This is feature 1 and feature 2. And this is the bias. You can say B. B is bias. Okay. So you have feature 1, which is like 0.05, and you have feature 2, 0.1. So this is, and you can see to each function, to each portion, there is a weight. So it's here is 0.2, for this one is 0.3. So you will just, for this one, if I calculate H1, What I will do, I will just multiply these one 0.05 multiply by this because it's coming here. I will multiply these two and add, and then I will multiply these and these because you can see the arrow. It means that this has this much impact on this H1, 0.05, and the feature 1 is 0.1. And there is a bias. You can see there is a bias. You can add 0.35. Do you have, are you getting this portion a little bit? It's a little tricky. Mathematics is there.
Yes, sir. It was clear.
Okay. So see, for example, for H1, only calculate H1. What will you do? You will have like that means 0.05. It's 0.05 multiply by this value 0.15 plus, now there is feature 2, 0.01 multiply by 0.2. You can have 0.2. Now plus, there is a plus, and then you have your bias. What is your bias for this feature 1? H1 is 0.35. So it's 0.35. And you multiply. So this is for the H1. You can have this one, X1. Now, find out H1. Now, which formula I'm using? I'm using sigmoid. So now the input is this one. I will put this one 0.35 into the sigmoid function. So I will say 1 divided by 1 plus e raised to power minus this amount 0.3775. So you can just add this one and it will be 0.396. So this one is the hidden layer one. It has this much impact on your first. For the second, you will add the same, and the third, fourth, it's up to you. If I have, for example, if I go here, you can see here. So this is the weight for. This could be one of the hidden layers, one of them. So you can see if after adding this one and the biases, I can understand that this has this much impact. 0. Just a second, it should be somewhere here. Okay. 0.4 you can see, or if you add more you can have, or you can just make here layers, so you can have here more 0.4, but it's minus 0.22. It's up to you that how you are going to, so you will just calculate each step like this. For example, for ReLU, again, it's you can see, do you need to practice or no? Can you do it for H1? Are you sleeping, guys?
No, teacher.
It's easy, sir. We will just multiply that and then we will get the summation. Am I right, sir?
So yes, you are right, but let's do it together because your classmate might not have full understanding of your right. Just a second, let me go to your insert. Where is my? Oh, it's here. It's on here. Okay. So for this one, I will just calculate x1. For x2, I will say x2. Oh, x2. Why I couldn't get? Just a second, let me go again. An equation. Okay, now I can write. So I have x is equal to 2, which your classmate said is very easy. Now I will see this in here. Which features goes here? I said that from h1 0.05 times what? What is the weight it coming here? It is 0.2. It should be, you can help me, anyone. 0.2.
Okay. 20.
Oh, sorry, 20. 20. Now, then plus, now for feature 2, what I will say? I will say that it is 0.1.
0.10 multiple 0.3.
Well done, 0.3. Well done. Now this is how I will do it. Now I will just, it's up to here. Now I have this one, plus there is some bias. If you go and see the one in here, there is some bias. Bias is 0.6. So you can see 0.6 is bias. Now if you multiply everything, can someone do it fast? Can you please multiply and add this one and add at the end this? What will be x2?
Okay, so
X2 will be something for to the class, okay? Will be some, what is it?
it's equal to 0.64.
0.64, for example. Okay. Now this is your, now to calculate sigmoid function, I will just put 0.64 in this, either this one or this one. It's just the same. It's divided by this e raised to power minus x. So I will just put for the one. I'll say that h2, now h2 is equal to 1 divided by 1 plus e. E is the, what is e? Does anyone know what is e?
E is Euler number. It is 2.
Yes, you're right. Yes, you're right.
87 like this.
something. Yes,
Yeah,
you're
yeah.
right. Good. It's Euler number, so it is 2.71 and raised to the power. Now, raised to the power what? It's e raised to the power, this one, 0.46.
0.64.
So now if you calculate this one, now you can understand how much impact H2 has, so this feature has. So the same it goes. So you can have multiple of features and multiple weight, and also you will have your own bias. Based on this one, you can do it like here. Okay, I think you understood.
That
Now you are
shouldn't
perfect.
be negative, teacher. Sorry.
Yes,
It
please.
shouldn't be
Atifa, can you come
negative.
again?
0.64. It shouldn't be negative. Or
Oh,
am
yeah,
I
yeah,
am
yeah.
I wrong?
Yes, you are right. Absolutely right. Well done, Atfa. You are very observing, very good. Okay, that's perfect. So it should be minus because in formula it is e raised to the power minus x. But if you go with this one, it's plus. But in here it's minus. Well done. Okay. Thank you, Atfa. So you can calculate and you can get something. So this one is sigmoid function. Then what is now? It's there is a ReLU function. It's up to you which one you. The ReLU rectified linear unit. It's also called ReLU. Simple and efficient computation, which is mostly deep learning models. The function returns 0 if it receives negative values. If there is any negative input, it will directly give 0 because it will take maximum. But for the positive, it returns the value itself. So what is it? So you will have f of x is equal to maximum of 0. If it is negative, maximum of whatever you have. For example, you will get this amount here, like it was 0.64. It will take the maximum of 0 and the output that you are getting from your function. It will take the maximum. If it is minus, so it will give the 0. Otherwise, it will give you the number that you got it from here. So this is how it looks in real world. So if it is negative, so it's all 0. But for positive, it will give it itself. It will be itself. So for the same, you can see you have like this is now 0.05. It's 5. Let me make this one. Okay, it's 0.05 times for this h1. I can say 0.05 multiplied by 0.15. Then I have this one. Let me make it small. So 0.1 multiplied by 0.25 plus the bias. Bias is 0.35. You can see here 0. And now I got 0.3775. I got this one. Now I will, for ReLU function, I will use max of 0 and 0.37. So I will get h1 is 0.3775. So I can get now this feature has this much impact when I'm using a ReLU function. But for then what, how much was it? It was, if I use sigmoid function, because it's the same, yeah, 0, you can see 0.3775. And if I use sigmoid, it is having this much value 0.396, and it is 0.3775. So, and the question is that which one should we use? It's all about it's all trial and error. first of all, you might hate sigmoid, then you say, no, sigmoid is not giving you good results, so you can use another function like ReLU, maybe another function, hyperbolic tangent function. A hyperbolic tangent function is a mathematical function having a scale like s. It's also the same, but in here the boundary is from -1 to 1. It's just like the tangent. So like sigmoid function, stronger gradient than sigmoid in the large range, but better for optimization. So if you are going to use optimizations, hyperbolic tangent is very good. So the range is here. So this is the formula. After you are adding these ones all together, then you will put it into hypertangent formula. So e raised to the power x, you can just see all of them here, and it will give you 0.60. Do you have any question, guys?
No, teacher.
Okay, that's perfect. Then we have another function, it's softmax. Now for these ones, now there is a question that if there is multiple of features, like there are multiple outputs, how should I do it? So there it comes, the softmax function is a mathematical function used in neural network, especially in output layers for multiclass classification. If you have multiple of something, you will use this softmax function. It converts raw scores logged into probabilities, making it easier to interpret which class the model is most confident about. So you have like in here, this is the function. You can go from 0 to like this. So this is exponential of xi divided by summation of exponent raised to the power xij. Okay, now for example, you have here features like this. You can see you have x1, all of them. Then you will put into this feature, this function. Now I cannot find that website site. I forgot. What was it? Neural network playground. Maybe it is not this, not playground. No. There is a very good website. I forgot the name. No, for images. Because with images, you could. This is not good. Maybe because Hugging Face. It's just like this. No. Let me see in the break if I could find that one for you. Okay. I forgot the name. I don't know what was the name. So if there is multiple of these features, you can do it like softmax. For example, you have output of cat, dog, lion, tiger. So if to understand which one has more impact, you will use softmax function for this one. But for these ones, mostly we use these features. ReLU, hypertonic is used for binary classification for positive and negative, yes, no, and this one. So you can have yes or no, or is it positive or negative. So binary, for binary, mostly we use sigmoid function for to understand cat and dog. Only two things, cat or dog. But if you have multiple of images and features, then you would use softmax function here. Have an activity. Are you going to do it here? Can someone, should I put you in a group?
I think let's do it together, sir.
Okay, let's do it together. Okay. So you will do it. I will just type it now.
Okay, right.
So it's for sigmoid function. So it's for sigmoid function. Everyone, please help me out.
Okay.
Please put the formula for sigmoid function as well, sir, here.
Okay, let me copy paste the formula of softmax function. Where it is here? Copy. Let's go to here, and I will just put paste here. Now this is the formula for this one. Okay. Now first of all, what I want to do it x1. What is my x1?
X1 is 0.6, teacher.
Okay.
Yes, teacher.
Feature 1, okay, 0.6. 6 multiply, what is the weight?
0.23.
Okay, 0.23 plus. Okay, what about feature 2?
0.7.
Okay, 0.7. Everyone, please just open your mic if you.
0.34.
Okay, let me make it 0.7 multiplied by. What is multiplied by?
0.34.
Well done, 0.34.
And
Okay,
then again
anyone else?
plus.
Mariam?
Feature number 3 is 0.8 multiplied to 0.87. Multiply
0.87. Good. Now what is it? And what plus? What should I add?
Should plus bias.
Yes, what's the bias?
Bias.
Yes, the bias is 1.
No. You can see here.
I think it's
One shows bias.
0.7. 0.7.
One shows, this one is showing you the bias. It's the value for bias. So you have 0.7. 0.7. Well done. Now if you can you someone do the calculation for this?
Sure, why not? Let me just go through it. 0.6.
Let me see for this one. For why can I not? I don't know where. Yeah.
Cool. 1.772.
0 point?
One point.
Mariam, are you watching movie?
No, it's not me, sir.
Who is it watching movie? Okay, what is 0 point?
It is 1.772.
1.772.
772.
Oh, after this one, now how can I calculate H1 hidden layer? So for hidden layer, I will have H1, which is
H1 equal to 1.
1 divided by
1 plus E power -x. Negative x, minus x.
E, which is 2.71 whatsoever,
Yeah.
raised to the power minus 1.772. Yes, you are right. So this is, what is the answer? Can anyone give me the answer for this one also?
Let me just copy it.
Let me write it a little more cleaner. 30. One divided by 1 plus 2.71 raised to the power 1.77. Yes. What is the answer? 0 point what? Is it difficult to calculate?
It is not difficult. I cannot find power in my calculator.
Okay, there is something. Okay, then you can do it. So there is something. That is the value for H1. For H2, you'll again do the same mathematic. You can find the hidden layer, the value for this one, and then for output, there will be another function. For example, maybe ReLU function. So you have this value of this one is here. So sorry, it will be here something value, and there will be some weight. And then you'll do the same. You'll go for this one. and then you will find out what is the output, whether is it cat, dog, what is it. So based on this, it works like this. Okay, do you have any question?
No, sir, no question.
So you can do it for feature 2 at home. At feature 3, you can do it later. So you can just find H1, H2, and H3. Then again, there will be some weight for example, this this if I copy paste, so there could be some weight for here. So I have the value from here, so I have some value, then I multiply this value, and the same value will come from here, and then I will use the function, maybe this one not softmax, maybe I'm using this time ReLU function. I will just put ReLU here. So then it can be. So now, just to not get confused more, let's read the features and then we come see the architecture. Then we will see in the code how we can do it in the code. It's very easy also. Okay, ReLU is like from it will like 0 and infinity. It is from 0 to 1 and -1 to 1. So the boundaries are here, the range. And you can see is greater than 0, smooth curve, saturation at extremes, like smooth curve, saturation at extremes. So it's just because you have from 0 to 1 and -1 to 1. So it's a bounded curve. So centered, zero centered, no, yes. So you have here a zero centered also here. You can see here these ones. So then very slow, ReLU is very slow, moderate and moderate. The others are very good, a little bit better. Strong for positive input, zero for negative. For large, vanishes for large. If there is data is like large, so it will disappear because you are putting it in between 0 to 1. And this one will be X, and you can see hidden layers. Now the problem is that let's see how it works in real world.
Sir,
Let me,
all these functions are using an neural network, right?
yeah, it's up to you.
How
Yeah, it's
can work together? How the IT engineers do all these? I don't know.
we can now I can show you how it works. Let me just give me a second. Let me take a Jupyter. I have already uploaded the codes for you, but still let me open my Jupyter notebook. We can go together. We can see how it works. So it's already here. You can see here. If I see you the demo, show you the demo, see you the demo, show you the demo. Here I will have a new, for example, here I will make a new one. So you can see all of them I have already done here. We can see here. But how we can do it, we will go and see a bit by ourselves. So for using like deep learning and others, we use two libraries we can mostly use. One is TensorFlow. So this is an end source for machine learning platform and deep learning. So you can have all the models you can have here. This is the model that I'm using. This is it's really the same, like this code, exactly the same code that I'm taking from here. And then there is another one, PyTorch. So you can see PyTorch. So this is also for deep learning community. So you can have many things here. So if you need to use machine learning and deep learning, so you can use PyTorch, Python Torch, or you can say PyTorch, or you can use TensorFlow. So you'll just say import TensorFlow as TF or whatsoever, then you can have this one. If I'm doing the same, this is exactly what I have taken, and this is in here already. So we will go and see how it works in real life. So first of all, as here, I will just say some import TensorFlow. I will say TensorFlow as TF. It's up to you as whatsoever. For my shortcut, I use TF. So I will say also I'll say from TensorFlow dot keras. So I'm having some libraries that I want to get it. Import layers and modules. So I will have some modules and layers. So if I run this one, And for this function, for this one, I'm using this this dataset. It's built-in dataset. You can see. So modified National Institute of Standard and Technology is a famous large dataset written. So it's just like hand digit. It's just numbers from like 0, 1. So someone has written like this, someone has written like this. So it's just like handwritten digits, which is like 70,000 handwritten and from 0 to 1. And its format is 28 by 28 pixel. So it's already inside. It's already they have done, and they have set the model. So just if I write, I don't need to download anything because it's just here. And for even for fashion, I have like fashion MST. I have this one also. So they have some for fashion they have, which I was asking in the class. So this is data set for fashion. You can even take this one. You'll see. So it has like some features. You can see there are plenty of codes already done here. So you can see maybe this person has done very good one. Let's see if is it good or no. So there is some, yeah, this is neural network. So you can see accuracy is 9. Okay. Final is okay 90.5, which is very good. Accuracy is 90.5. So they have already trained, and you can see all of them here. And the same I was showing you about this. So I'm using this not this fashion. I'm using the hand digit MNIST data, which is about handwritten digits. So how it will learn, we can see here. So I will just say that I have X train, I have to train the model, and I have Y train. And then from here I have test X train, test and Y test. So you have one training and one for testing is equal to, now I will call this library tf dot errors dot datasets. It's already in this dataset. From here you can see from this one, I say in dataset in answer. So you can already find this here. It's already given here. Everything is here. So this is the images. You can see all of it here. So you can say download simple. So you can directly ask from here. You can say TensorFlow. I'll go here. Parent. You can see code is already and everything is here. So if I pen parent MIST, so this is the images. So you can see it works like this. So you have like 4 or 5, it will understand everything. But let's do it by ourselves. So I will say dataset NIST dot lot data and enter. So it's working. Now I can have normalization of X train. Maybe I said divide is equal to divide by X train. Normalize everything. X train divide by 255. And the same I will copy and I will paste for X test. I will normalize everything. Then I will have, now I will make a module, like you can see module. I can copy paste this one, or we can write it together. We can have some functions. I'll say module. I have my module. I can say modules dot sequential. That should be capital sequential. And I will say, now I can here, I will say I have layers. I can have here, you can see layers dot flatten. If you don't know some of words, it might be new because we can cover it in the class. I have some slides for this alt flatten, what's the other one, but I want to show you how it works. You'll say 28 because you can see here it was 28. If you know, I'll come back. It is 28 by 28. So I will just write that my images are 28, comma 28. If your image is like 256, you just write 56. If it is the size of your image, what is it? So you'll just write here that one. And it's because it's 1D, because it's only 1x, there is no any 2D or 3D. So I'll just say that it's 1D. So it's one side. So you can read all of there, but it's here in another language. It's 28 by 8. As it hello, okay. Then I can have, now I'll say layers dot dense. Dense is like 128 neuron, and activation. Now I will write, see, I can write only activation. Activation is equal to, now I can say here ReLU. It's up to me. ReLU or sigmoid is on my hidden layer. Who was it? Did I answer you? You will just write here ReLU. ReLU, and the other one, maybe if I need more, so I will say that layers. You can see here layers, maybe ReLU, maybe another one. So it's up to you. Let what you, or maybe I say ReLU to dance 128 activation. Maybe you can use two ReLU function, like make 2 times. For example, in here you have 2 hidden. Here you have 1 time, it will do it. Another time again, it will use a function of ReLU, so that it should run hidden more and more. What we are doing with our here with our TensorFlow. So I can add more hidden layers. So it's up to you how much you are going to do it. So you will just do it from here. If you need 2 times, you will just 2 times. If you need 3 times, you can write 3 times. It's up to you that how many layers do you want to have inside your this. If it is 3 hidden layers, so you will add 3 times, and you can change accordingly. So you can have 3 layers. It can be, the first one can be ReLU, then it could be sigmoid. So it's up to you that which layers or how you are going to put it. So if, for example, if I put 3, how it will work, let's see whether, and then there will be an output, because as I said to you that output is from 0 to 1 and 0 to 9, there are 10 outputs. So this is multi-classification, multi-types. So because it's not 0 and 1, it could be 0, it could be 1, it could be 2, 3, 4, 5 till 9. So it's multi-classification, and for that one I was using what softmax function. So I will say that layers dot dense, I have 10 output. I can say that how many outputs do I have? I have 10 outputs. So if you count from here, it's from 0 to 9, which is 10. So I will say 0 to 10, and then activation function now I will use here as softmax. If you have somewhere any problem, you just let me know, because I know that there could be something difficult. Layers, comma, where I have put comma. Here I need comma. Here I need comma, comma, comma. Oh, here I need comma. Okay, now it's working. You can see. What's arguments when segmentation? So there I can have 1. Okay, let me have 1 here. Okay, now because I'm using segmentation, so I have like flat 1D, so I have only 1 there. But for the others, I can put it, I can show it in CNN, which I have used many of these one. So then I can use module.compile optimizer. There are some keywords that you are putting, and I will show you what are those in the slides. But for now, you should just try to see how it works. And loss, there could be loss function. Losses in there we had like binary, like cross entropy, and there are plenty of these ones, so we can see all of them in our slide. There should not be any typo because it will give you an error. And matrix. Hopefully there is not any typo. Yeah. I compile and now I can fit my model.fit. If I say x train, comma, y train, equal to 5. So now it's going to train your model. Now, because I said to you that there is some typo mistake, let me get exactly the name for this one. Entropy. This one was spelling mistake. Now in here it's training your model. You can see now it's fit. Now it's giving you the accuracy showing you everything. I said 5 epochs. It will just 5 times. It will have inches. It will understand everything. But this is very small data set, or you can say very easy one. But if you have big data set, it could take you 1 day, 2 days, or maybe long time to train your model like this. You might need to use GPU even, not CPU. So now it's already done. So now if I just try to understand that what was my test loss and my test accuracy, I can say model dot evaluate, and I say that X test. Now I have to check whether my X and Y are giving fine result or no. And I can see print accuracy. So now it's 0.975. It means 97.5%. Its accuracy is 97.5, which is very good. So you can just imagine that if you have an image, so 97. If you have 100 image, so 97 times it is giving you correct answer for this. So it's giving you a good. For example, if you have some prediction, so now we can see some of the examples like prediction. So I can say predictions, I can see some images and its prediction model dot predict. So I just want to predict whether it's giving me on what an X test. Now I'm not using my X trend, I'm using on my testing that whether the testing is correct or no. So I will just say some random, for example, for I in range, maybe 5. There should be 5 images. Give me, and I'll say PLT show. PLT I'm show. It will show you the X test and okay, X test. Say maybe in color gray, maybe clean, and then I can say PLT title. There should be some title, and it should be written as F. So just I can too much, so I can just I forgot. Let me right here. It's too much. I don't want to. So it's predicted and it's giving you the true test and also the predicted value. What was the real one and what was the prediction? Whether the prediction and the image were same or no. So you can say plt dot access or no access. I'll say plt show, just show me whether it's there or no. Now plt and import matplotlib dot py plt. Yeah. What was this matplot? Plot. Yeah. Oh, if you see, I have not, NP is not here. So I'll say it's an array. I'll say import and numpy is NP. You should, if there is any error, you can. Okay, now you can see my true was 7 and predicted is also 7. You can see the image was 7. So the prediction is showing you correct one. The true was 2 and the prediction was 2. So it is giving you the 2. It was correct. Because I'm doing it in S test. It's not on my training. I am just giving it randomly. It's like X. My true prediction was 1 and it was also 1. Prediction is also. It was 0 and it's 0. It was 4 and it was 4. So it means that my model is learning the trend very good. You can see all of them here. Do you have any question, guys?
Teacher.
What was it? Aisha, did you say yes or no?
No, teacher. I
So
know
this
it
is
was
how it
clear.
works. You can understand now. You can see that how system learns. So you had some like ReLU function here. You were doing calculation here. In here you are doing all the calculation. But in here you will just say to your system that ReLU. My activation function is ReLU. So, and this is the dense layer. My hidden layer hidden layers are 128 neurons. So you will just see all of them, and it will there is like 10 outputs. It will, and you are using the softmax, but in here you had this formula for softmax, this one. But in here, because it was used, you can see it was used for multi-class classification. It was because you have from 0 to 9, it's multi-class classification. You are using here softmax, and then there is some add-on. These ones we will see in what are those, how we can do it then in our slide. And then we have like we can see our test accuracy. When you are testing on your accuracy test, accuracy is 97.5. It's not your trend accuracy. It is just you are randomly, or you are seeing that how much it is working. And then you can see your true was 7 and the prediction was also 7. It means that your system is learning properly. So it will understand. Now if you just try to manipulate with this one, so it can understand it very easily what it was the image. So now we can easily learn how to read from images. So it's just how it works. I will find out for you in the break. Maybe that one was there was a very good website. It was showing you on images how much probability was there. I just forgot the name of that. Okay. So if you don't have any question, so now we will go and see these terms. What was the terms that I was using here? What were those terms, and how you can do it? For example, in here we had some. I used epochs here, epochs. Maybe this laws. What was this one? And others we will see all here in our presentation. So before going in deep to this network architecture, I will have a break of 15 minutes, because I will just, once I start, I don't want to have interruption. So just take your break now, and then after the break, we will come and we will see it here. Okay? If there is some questions, what about tomorrow? Zahra, okay, you can see. Do we have practice tomorrow? Practical part tomorrow?
Tomorrow we are
Oh.
off, sir.
No, we are off. Someone has written, sir, namaz break. Oh, see, I didn't read the message, but I knew that it's your, so you can have your break. Okay, let me. Okay, you can see this is a demo. You can see this one is like, here is a bias. You can see a bias here, a weight for this one. So for this, there is a weight. So it's giving you, and there is also a bias. See the bias here. Here is it's giving you, and then it will show you that whether it's, what is it? Is it ladybug? Is it pizza? Is it bell curve? So it's all interconnected with each other. So we can go through these one by one in here. Okay. We will start the network architectures. We have shallow neural networks and deep neural network. So in shallow neural network, we have only one hidden layer. You can see from here. So is which one was sequential, which one I was doing it. In previous example, it was here one neural network. In here, if you see, there was only one neural network. But in deep neural network, you have multiple neural network like features. You can see here, and also you can find out here also. There are plenty of neural networks. You can see there is 1, 2, 3, and like this 4. So you have 4 neural networks at the same time. So shallow is one or very few, but in deep learning we have many. We have two, even 100 plus neural networks we have. So we could have plus of 100 plus neural networks at one model if we need, if our patterns are very complex. So it can learn simple patterns, which was for 0 to 10, which was handwriting digit, but can learn very complex patterns, images, languages, etc. And computation is fast because you are using only one hidden layer, so it should be very fast training and low memory usage, but it requires more computation and data. So as I said, that there you might need some GPU, even graphical processing unit for your this deep learning project. So example is linear regression, simple classification, but in image recognition, translation, image recognition, speech recognition, these all can be. So it's easy to train and less prone to overfitting, but it is having higher accuracy of complex tasks and more expensive because you have to use GPUs, so and computation will be expensive based on those one and more expressive. So harder to train and risk of overfitting without regularization. You may have overfitting, but in here limited powering power. So you can do it with your CPU. You don't need to use GPU or any other uh, processing. So fully connected layer dense is a fully connected or dense layer means, so if you remember, we were using here dense. So in here, we were using a word, which one was dense. So it means fully connected or connection, so hidden layer, so dense. You can see here dense. So what is it? So it is a fully connected or dense layer means every neuron in one layer is connected to every neuron in the next layer. So it means that in here, this neuron is connected here, this is connected here. So all of them are interconnected and it's connected with each other. But there could be sometimes that one is not connected. Maybe you can find here. So this is not this is a fully connected. But if we go here in our TensorFlow, so this is, if I, for example, see here, this is not connected. If I connect all of them, and in here also this is connect, in here this is now is fully connected. But if there is not connection, there is less, you cannot say fully connected. It's just hidden there. It's not fully connected layer. As you can say that it's just like hidden layer or something. But a fully connected layer is like every neuron in one layer is connected to every neuron in the next layer. You can see here, this is connected to here, this is connected to this, and other, and so on, all of them. So each connection has its own weight and biases. So you can see here also in this one. So it is having each connection in, if I put it here, so it has a bias and also a weight here. For the same for here, it has a bias and also a weight. You can see all of them here, a bias. So each one has a weight and a bias for here. If I click, maybe I can click twice. So it's all here. You can see each one of them, bias and a weight, bias and a weight. So commonly used after convolution or recurrent neurons to combine learned features and produce a final prediction. So you can see here, this is convolutional neural network. So it has x is equal to wx plus p. So you can see x is the input vector, weight of matrix is w, which we were doing, and bias, and output is this one. So it's just the same formula as we were doing it here. So this is here the same formula. So for example, now you have like here how to construct a neural network. You have like four features: humidity, temperature, illusion, and air quality. So there is 1, 2, 3, 4. Of case one, map independent variable features to input. So this one will be your inputs: humidity, temperature, illusions, and here. So here we have 4 independent variables, features, or attributes. So you can say, someone can say variables, features, attributes, they are same. This is the number of neurons in the input is should be 4. So now we have 4. 1, 2, 3, 4. So in here 4. Now we have hidden layers. These are the hidden. The number of neural networks in the hidden layers is a trial and error. So you can add more or you can make it less. It's up to you, because sometimes if you make it more, still it could give you bad result. But less might be better. It's trial error. You can play with this. If to make it more or less, it's up to you. So it's type of practice. So you can specify any number of nodes or neurons in the hidden layer. So you can have like 52, which one 128 I had in here. I was specifying here in this. You can see here it was 128. So I have specified the neural network here. Then at the end you have so it would be now case one is binary classification, when you have two target categories in the output. So it could be positive or negative, binary, only two. So it could be 0 or 1. So the number of nodes in the output layer depend on the number of categories on the output variable. So in the binary case, only one node will be specified. So you will have only one node because it could be positive or negative. But for multi-classification, it will have more nodes. So you have 1, 2, 3. So it is multi-classification. When you have 3 categories of, so you have 1, 2, 3. So you can have 3 outputs, these, or these. So the number of nodes in the output layer depend on the number of categories in the output. So you can see here in my this here, if I just take this out, you can see here this is the output. So this is category multi-class. So it could be this, it could be these, it could be this, it could be this. So if I open, I say show details, so I have 10 outputs. If I see here, so this is softmax. You can see softmax function. If I click, so it's here. So it's getting from here. And this is the formula that it's working. So e raised to the exponential of this one divided by whole exponential. Which one we are giving it in this formula, softmax function. So it's all softmax function. You can see here, this is softmax because we have multi-classification. And for this, so if I go to output, so this is 98.4% sure that it is ladybug. If I go here, the image is ladybug. But if I make it, for example, I should get out from here. Maybe I should just take it out, put any other image here, maybe for pizza. So now for pizza, it will again go here. And now how much it is? Now it is like 99% sure that it's pizza. It's showing you pizza. So in here, these are the weights. They have calculated everywhere. There is a bias, so it's bias rated. And now this is the softmax function. You can see the softmax function. So this is for one. This is for the other one. So you can see all of them. So this is for this layer. So for the first one, if you go from here, it is for the first. You can see for the first. This is for the second, third, fourth, fifth, and this is the here for pizza, for this one. So divide by this. So you can see all here. But if I change, for example, I should cancel this one. So I put car. So now this is red, green, blue channel. So you have like 3 channels. If I see sport car, how much sure he is? 96% he is sure. But for others, if I say orange, how much is sure? Is it sure something? It's 0.0033. So this much percent is saying that it might be this image might be an orange. For pandas, for espresso, it's 0.0126 for this car. Although it's car, but there are some percentage that they are saying that it might be this was 0.01. So you can have very less amount. For boiler, this might maybe we can see some this one. Let me close this one so you can have like this. Let's see, is there any change? So red panda is this much. So how much ladybug? So there might be some percentage. How much? 0.017%. You can say not percent. It's 0.0176. And if I say in espresso, it is 0.12. But for red panda, it is how much? Sure. It is 95% sure. So it is means that it's 95% sure that it is this picture belongs to panda. And the same it goes to this function. But if I just cut this one, for this one, maybe you can see here, this is the bias, everything is here. So it's taking from each one from here. This is one, so you can see all of them here. We can see it later also. So, and for each one, so there is a weight, a bias for each function. And for if there's classification and multi-classification, you have softmax function. For binary, you have sigmoid, ReLU, it's up to you. So this is how it works. Okay, you can read this also. Do you have any question, guys, so far? Are you sleeping?
No,
No
teacher, we are
question.
here.
Any question?
No question, teacher.
So we have an example here. For example, this one we can just solve. You can see for this one we have this one xi, the same, it goes the same function it is. So you have like this feature. First feature is 0.05 multiplied by this weight plus this one is 0.1 and the weight of this one is 0.25 plus the bias, and you get some h1 and then it's here. From for this one, now this is okay, this one is for the other one for this H2. So for H2, they have done like for H2, what is it? It's for this one 0.05 multiplied by 0.2, and then for 0.1 multiplied by 0.3 and the bias. So at the end, you get H2 is this much. Now you have this. Now for to make the output, we have like now we have this all of them. Okay. Now for H2, there is we have H1. Where is H1 if we have done it? Here H1. So this is for this output. We have H1. What was H1? We have H1. We have counted here 0.59. So we have 0.59 multiplied by 0.77 plus we have for the second one 0.65. So we have 0.65 multiplied by this weight. And now we are getting for O some value, and then we are using a sigmoid function. Now this much is 73.76%. This could be sure that below image or this root belongs to maybe an apple or a cat or a dog. So it's up to you. So this is how it gives you the percentage that how much, what should be the output and what is the output. So it will connect this weight and biases. So this is the whole picture of for this the one that we are doing. The one that we are doing here also is the same. So it is calculating for it's calculated for this one. For this, it calculates for this image. Then for this image, it will have some values. It will go for the other one because it will do the same. And then it will go to this one. It's giving you the same. There is some bias and there is some value. And it is for the other one also. It will get from the previous one. From previous values, it will add on. So it's just the same as here. So you have this, first of all, you will calculate this one, then you will calculate for this one, you will calculate based on what you get for H1 and H2. So I hope that it should be easy. So now it comes to one of our good convolution neural network, CNN. So convolution neural network is a special type of neural network designed to process data with a grid line structure, such as images 2D and audio spectrograms. Instead of connecting every neuron to every input like a fully connected layer, CNNs use filters to detect local patterns and build up more complex. So to understand here, we are not using fully connected layers. What we are using a filter. Filter could be in here, this example. If I show you, this is the filter. If you like, let me go from the beginning. If I go for this one, now this is a small filter like they are using. So it will put this big image into small image chunks, and then it will transfer your data from here. It will take the most important ones and it will go here. You can see here, like here, it's all here. If I run, now see, it's learning small by small. It is like 3 by 3. So it will learn, and this will give you an output. This one is output. You can just see the output here. You can see the output. So it will learn, it will go to all your features. It will go to all your rows, row by row. Like it will give you 3 by 3. So if there is something useful, so it will take it. Otherwise, it will throw this one. The time it will reach from one filter, it will reach to here. Then from here, you will use another filter. So to understand this feature, so you will have this one. Let me maybe make it big. Again, it is now making it another one. So it is making your big pictures into small chunks, and it is getting the important features so that till the end it will understand what is and going to in here. It's again, if you see here, it's small. Today you can see this is into filters. So this is called kernel or filters that they are using in convolutional network. So instead, fully connected layer CNN use small filters. So in here, if you have this is your image, it will take it into it will put into binary, or you can say grayscale, like from 0 to 255, or grayscale 0 to 7. If it is color, so it will be 0 to 55, the numbers. So it will make it into small chunks, and from small chunks, it will going to learn the patterns. So you can see here, this is filter. So it will take this one and it will give you an output. For this output, it will be another, there will be. So to the time, it will give you 0 to 9. Convolution operation, a filter, also called a kernel, is a small matrix, 3 by 3. It is a small matrix. So it could be 3 by 3. It could be any size. That slides over the input. So it works if it goes from input, it goes like slides. It is just from this one, then the other one to the time it will reach there. So that slides over the input image. At each position, it performs a dot product between the filter and the part of the image it covers. So it will be a dot product. It creates a feature map, highlights specific patterns, edges, corner, and textures. So it will find out where is the edges, the corners, and textures. So reduce the number of parameters. If your image is like big, so it will just try to make it short. It will take the specific or important features or patterns. To preserve spatial relationship, learns local features first, then combines them for complex understanding. It will understand which feature has connection with what color. So for example, if you see here, in here, if your red color is like, you can see this is the red, so it will understand that this is all red. So it's for this one, it will green is here. So it will understand, it will go there, and it will just convert based on the color and the contact. It will learn what is it, first of all, what is the mixture of what colors are here. So it will understand all the things and all the patterns, and then it will start to go. Then after that one, then we have like, if there is like, there is a filter of this one, so we can use max pooling or this one. So for this filter, we will just see the maximum. We'll say that in this one, take only the maximum 9. For this filter, take the maximum 7. For this 8, for this 6. So it will just make take the important features, only the one that is important. For example, maybe maximum of this one. So I need this 9, maximum of all the kernels. So reduce the spatial size of the feature maps keeps the most important information, makes the model less sensitive to small features, shifts, and destroys in the input. So you can see here also that if I have here max pooling, so you can see this kernel is big. Let me run. So this one. Oh, it's not working. Okay. Okay, for this, you can see here in here maximum. So in here it is 0.16, 0.18, 0.7, and 0.56. So you have used max pooling. So it will, from this kernel, it will only take the maximum of this one, 0.18. If it will go to other one, okay, now in here it will take, there is 1.33, 0.99, and 1.22. So it will take the maximum 1.33. It will just make, it will go like this for all of them. So there might be, now in here it's 0, 0. So there is no any feature, nothing. So it will take the 0. Yeah. Now in here it is the maximum. It's what? 1.06. In here it's 0, 0, 0, 0. It's all 0. So now there is, so you can see when there is colors in here, there is colors, but in here there is nothing. It means that your feature is here. Your main features are here. Your main features are here more. So see, it will just take maximum of here. Now for this one, it's only taking one number. This 2 by 2, like for this 2.14, it's 2 by 2. It will take only 3, the maximum. For the other one, it's also taking. But in here, because it's 0, it's all 0. There is no any feature. So it might be the edges or something. But in here, which is maximum, so it is getting you the color. So it is how it works. You can use max pooling. So it will take from 2 by 2, it will take only the maximum of this 2 by 2. So do you have any question?
No, sir.
So in here you can see your input is 60 by 60, but your output is 30 by 30 because it's making it less. It's taking these features because at the beginning it was too much, but now it's only taking the maximum of this filter, that is 2 by 2. From 2 by 2, it's taking it only 1. So you can see all of them here. All of them. So you can see the output side, it's only 1 dot. So it means it's only like 0.16 there. So it will just write 0.6 in your output for this one. Then it will learn other one, like the same it goes here. So I will not say a lot because you will get confused. So this is how it is. And then you have types of, so you have max pooling, so you can take the maximum. For example, you have 1, 3, 2, the same that we are doing. So you can take the maximum, you can take average. So what average means? So it could be that you might take the average in here. So you will just take this one and divide by 4, and you will take the average here. Not maximum, you will take the average. So instead of maximum, you will take average of here. And global pooling, reduce entire features made single value per channel. So for each channel, you will just take one output, often used before fully connected layers. So it's just mostly we are using with max pooling or average pooling. Global is not that much used. So it reduces entire feature map, a single value per channel. So advantages of pooling is that dimensionality reduction, because it is like by 2 filter, it will give you only 1. So it means it's giving you smaller and faster modules. Also controls overfitting where there is not important or something, so it will remove unnecessary detail. In translation invariance, small shifts in image won't affect detection. So because you can, if you are shifting small by 2 by 2, it means that you are getting the maximum features here. So it's only 2 by 2 max pooling. It's not more. So you can understand. But in other kernel, it is like it's big. For your kernel, it is here. So it's by 3 by 3 for your kernel. But in your max pooling, you are taking it 2 by 2. So it's 2 by 2. But in here, your kernel is 3 by 3. So it works well with ReLU function, equation, and convolution error. So you can use ReLU function in here. So mostly in this also it is used ReLU. So you can see ReLU max pooling. In here ReLU max pooling. So it's, so you can read here also are extremely prevalent in modern technology. So you can read all of them. So this is all the formula that we are doing. Softmax, everything you can find in this website. If you read this documentation, you will learn about convolutional neural network. The example is here. You can see the example. So you have an image of this, like this is brain, image of a brain or something. Yeah, it's a brain. So it will make it into small features and then vectorize, and then you will put it, and then you get your output, because it could be normal, it could be mini Morgan. What's the name of there is some disease. So it could be this disease or this disease or this. So this is you are using softmax because there are many types of disease on this for this image. So you can get this. So you have an input, you have convolution, and then link, and then you have fully connected and output layer for classification. So this is for classification, and this is for feature extraction. Yeah, just keep in mind that there are two types, that you are taking features extraction, you are taking the important things, and then you are going to fit into your module. So for here, you will just take the features in here. You will just take the context, which is the everything you'll take, and then at the end, when you come here, it is your connection. Now you are done here. With this, you are done. Now you are using your connection here, fully connected layer here to take out and to understand or to work your convolution layer. But in here, it's all about feature extraction. So you are just taking the important details from these images. So this is feature extraction and classification. You will classify whether it's cat, it's dog, what is it. So it's here. So components, convolutional layer, activation function, pulling layer, fully connected layer, and output layer. So I think there should not be any problem for now. For this one, you can go and read this one out. Do you have any question so far?
No, sir.
So let me show you a demo. You can go to this demo. Oh, it's here already. I don't need, let me see.
Let's have a quick look at the model where we skim through the different processes. Feel free to skip this part. The model is pre-trained and has an accuracy of 95.4%. It will take in an input image with the dimensions 28 by 28 by 1. First off, we will perform a convolution with two filters that have a filter size of 5 by 5 by 1 and use
So in here they are using 5 by 5.
an activation function called ReLU. Next, we will perform max pooling with a pool size of 2 by 2 and a stride of 2. This is our first layer. Then we move on performing our second convolution. This time we will use 4 filters with the dimensions 3 by 3 by 2. The activation function is sigmoid. After this, we will perform max pooling as we did earlier with the pool size of 2 by 2 and the stride of 2. Then we flatten out the matrices. This is our second layer. Finally, we have a fully connected layer which outputs the predictions. Now,
So, what do you do? What do I do? Well,
let us see the model in action. We start with the input layer, which is a 28 by 28 by 1 dimensional image. These kinds of images are also referred to as grayscale images, as they don't have color channels, such as RGB images does. Don't worry though, the process is the same. If we break down the image to the pixel level, we see that each pixel is just a number in the range from 0 to 255, where 0 is pitch black while 255 is white. The image is fed into the first convolutional layer, which consists of 2 5 by 5 by 1 dimensional filters. These filters are often referred to as kernels. Each filter also have their own bias term. We will use a stride of 1 and an activation function called ReLU. The activations from the first filter will be mapped onto an activation layer. Now, let's have a deeper look at what actually goes on during each step of the convolution. In order to get the activation value, which is the pixel you see on the activation layer, we use this formula. Now, let's break it down. Since we use a stride of 1, we slide the kernel one step to the right on each iteration until we reach the end. Then we will slide it one step down and all the way back to the beginning. Anyways, if we look at the first term of the formula, this basically tells us to multiply the weights from the kernel with the overlapping values from the input. This will return a matrix with the same dimensions. Then we'll sum up all the values in that matrix and add the bias term in order to get Z183. Notice that this is Z183 as it is the 183rd iteration, which basically means that we have slid the kernel 182 times before this. In order to get the activation value, we pass Z183 to the ReLU function. ReLU stands for Rectified Linear Unit, and this is the function. We can visualize it to get a better understanding. Simply, for 0 or any negative value, ReLU will return 0. For any positive value, ReLU will return the inputted value. If we go back to our activation, which is negative 41.1665, we notice that ReLU outputs 0, since that is a negative number. In visual terms, a black pixel. We then slide the kernel one step to the right and repeat the process. Doing this for the whole image will give us the final activation layer from the first filter. Then we'll do the exact same thing for the second filter and move on to the pooling layer. As you can see, the first convolution outputted 2 images, or matrices. These are called channels. We will now perform max pooling with a pool size of 2 by 2 and a stride of 2. The pool size is exactly the same as the filter size. You will have a matrix with the dimensions 2 by 2. Performing max pooling on the first channel will result in this. Now, let's delve deeper into the pooling process to see what's actually going on. We start off by placing the filter in the upper left corner, exactly as we did with the convolutional layer. But instead of doing any heavy calculations, we simply extract the maximum value and slide the kernel 2 steps to the right since we use a stride of 2. We will then repeat the process and extract the maximum value. You might have heard of min pooling and average pooling. Basically, for min pooling, you will, as the name suggests, choose the minimum value, while for average pooling, you will choose the average of the matrix. In this case, the average of the 4 values the filter slides over. Moving back to our example, we will continue with the same process until we have covered the whole channel. Effectively, by choosing a filter size of 2 by 2 and a stride of 2, we have shrunk the dimensions from 24 by 24 by 2 into 12 by 12 by 2. Basically, half the dimensions of each the channels. Next up is our second convolutional layer. Here we will use 4 filters with a stride of 1 and an activation function called sigmoid. As you probably noticed by now, these filters are stacked. If you separate them, you'll see that we actually have 8 filters. So, what is going on? Well, there are 4 filters with the dimensions 3 by 3 by 2, since we have 2 channels from the previous output, which is this layer's input. We'll have 2 channels for each filter. In other words, 4 filters with 2 channels. There is also a bias term for each of these filters. Running the convolution outputs an activation similar to the first convolution, but since we have multiple channels, the calculation becomes slightly different. Let's have a look. First, we will place each kernel over their respective channel in the upper left corner just as we did earlier, and write out the formula for calculating the activation. As you can see, the formula is slightly different, but still very much the same. We will start with the first term, which basically tells us to multiply the kernel with the values from the input layer. This goes for both kernels. The next step tells us to add all the values from both matrices together. Now, you could do this in multiple ways, such as adding each term together one by one, but in this example, we will add the matrices together first and then sum up all the values. The results would have been the same either way. Next, in order to get Z1, we will have to add the bias term. Then, we move on to calculating the activation, which tells us to take the sigmoid of Z1, which in our case is negative 7.36. If you are not familiar with the sigmoid function, we will have a quick look at the function. By looking at the function or the graph, you might notice that the sigmoid outputs a value in the range between approximately 0 to approximately 1. Calculating the sigmoid for our Z1 returns approximately 0. We can see that by plotting Z1 on the graph. This means that the activation is equal to 0. We will plot A1 to the activation layer and move the kernel one step to the right and repeat the process again and again until we cover everything. This process is repeated for each of the filters. You might notice that some of the pixels on the activation layer are super white, while the activation value only ranges from 0 to 1 due to the sigmoid function. This is for visual purposes only. If we chose the conventional way of visualizing 255 as white and 0 as black, we wouldn't have been able to see anything on the activation layers. Anyways.
Du verwaltest Projekte an zu vielen Orten? Organisiere.
Let's move on. This is our last pooling layer, which is exactly the same as the previous one. We'll use a pool size of 2 by 2 and a stride of 2. This will have the dimensions for each of the channels and extract the most activated pixels. We'll then take the 4 matrices and flatten them out. We have now gone from 4 matrices that were 5 by 5 to a flat layer with 100 nodes. Each node corresponds to a pixel. In order to make the visualization easier for the next step, we'll hide all the nodes except the first and last 5. Finally, we have the output layer where we want to output one of 10 different predictions. This is the fully connected layer. Let's have a quick look at how these layers work. In our model, we have 100 input nodes and 10 output nodes. To simplify the explanation process, we will scale everything down to 3 input and 2 output nodes. A fully connected layer consists of input nodes and output nodes that are connected with weights and biases. Passing the input through the weights and biases will yield an output. First of all, usually, each output node has a bias term that will kick in later in the process. Then, we have the input node, which is connected to the output nodes through some weights. These weights are just numbers. You multiply the input node with the corresponding weight and add it to the output. You will do that for every output node and move on to the next input node. The process is the same. You multiply the input node with the weight and add it to the corresponding output node before moving on to the final input. Here, the same process is applied for the third input node before finally adding the bias terms. You might think that this is a tedious problem for bigger models, and it is. Therefore, matrix multiplication is used to tackle the calculations. So, here is the formula. The output matrix Z, which in our case would be 3.6 and 7, is defined as the matrix multiplication of the input nodes times the weights plus the bias terms. Now, you could add an activation such as ReLU or sigmoid, etc. to this output, but this wasn't done in our model as this was the last layer. Let's get back. If we scale everything we just saw up and run the input nodes through the final fully connected layer, we'll see that the model predicts that the inputted image in the beginning is 7. Exactly what I thought as well. Please make sure to like, comment, and subscribe to the channel if you get some value out of this video.
I will give you a very simple explanation.
Okay. Do you have any questions so far, guys?
No, sir, it was clear.
Okay, that's perfect. So now,
Yes.
when we are done, so now we are seeing how some of the why understanding the pipeline matters. So let's see the pipelines a little bit. A good model is not just about architecture. Success depends on every step of the machine learning pipeline. So if you are doing this, writing some part of code, it does not matter for like it could be that you have done the architecture part, but there are some keywords, key points, or some things that you should always try to keep it in mind. So in real world, AI system requires clean and well-prepared data, proper training and evaluation, awareness of limitation and biases, understanding the pipeline helps avoid. So you have to be sure that there is no overfitting and underfitting. What are those? We'll study now. Wasted computation and power performance, ethical and fairness issue in deployment. So you have data, raw data, and from various sources. You have this one, then you are doing pre-processing, model selection, and training and validation and evaluation and final output. So in here, you are doing the same. You are doing normalization, standardization, processing features that you are doing. Like if there is some other things that you will do it. Then model selection, what you are going to choose. Is it machine learning? Is it random forest in a decision tree, canyon, yes, never, and there are plenty of things that you are doing. Then you will choose, you will do your training and validation, and you will see what is your output, how it's performing using confusion metrics and other ROC, other graphs, many things, other things can you do it. AUC. So these are, and then you have your final model ready here for development. So you can see data, pre-processing, clean, transport, and prepare, and model like neural network training. You will see and measure performance using F1 score, accuracy, and other ones, precisions. You had like precisions, F1 score, accuracy, and one other one, I forgot the name. You will use this confusion metrics and these matrices, and then deployment is then you will see your trend into real world application. So then you are going to make application. So data processing, as you know, ensure clean, standardized, and high quality input helps the model learn effectively and generalize better, prevent instability and biases during training. So you have normalization and scaling. You can have mean and max scaling, standardization, z-score, which we are having in mathematics. Encoding categorically, if you have like categories like green, yellow, or something, so you can use one hot encoding. So you can put it one hot encoding is like 1 is present, 0 is not present. So into numerical format. So you change your category into new numbers, because our model understand numbers, not the images. Even if you have seen here, if you have like noticed here while we are doing here, so our images in here, everything is changed into number. So if I take this one and I open maybe this portion, so now this is all numbers. So these are changed into numbers. So that's why we need to use this one, because it's just that this computer understand numbers. So handling missing values, then you will see missing, manage incomplete data to avoid biases or training errors. Of course, you can use imputation, median, mode, or interpolations, remove row removal, everything that makes you perfect for you, you will do it. Then you have data augmentation. It is that increase data diversity to improve generalization and reduce overfitting. Like what can you do? You can image flip. You can flip the image so that the rotate random curves, noise addition, tokenizations in natural language processing. So you have an image, for example, of this beer, then you have to rotate. You rotate, for example, maybe 60-degree, or you maybe flip or something, so that the system, the machine should understand that this should understand or should take out all the or patterns from this image. You can use data augmentation for these purposes. So then we will split data into training, testing, and validation. So in training, as you know, that used to train the model, mostly it is 70 to 80% of the ratio. When you have test, 20 to 30%. You will check after your training, you will check your model that whether it's working or no. Or then you have 10 to 15% from the training. You use validation set used for tuning higher parameters or preventing overfitting. So you just validate your training while you are doing training. So you validate 10 to 20% of your training data, so that you should understand that there should not be any overfitting or hyper tunings. You are changing the amounts ups and downs, so you can play with those ones. So elevate model performance on data it has never seen before, helps detect overfitting, that when the model memorizes training data instead of learning. So there could be sometimes that the model is memorizing what you are giving. For example, it's like cramp, like you are giving to a student that you should read. So he will already read the words, and when you ask, so it will give you the same. But if you just change the question a little bit, so he will stop. He cannot answer your question. So that's memorized, and instead of learning. We want that it should be machine learning, not machine memorizing. Machine should not memorize what we are giving. We should learn the patterns. So ensure the model generates well to the real world scenario. Okay. So this is validation set. So it's a subset of training used to tune parameters, adjust model design, and monitor the performance during training without touching the test set. So in here, if you see here, so we have data. This is training and testing. But from the training portion, we take some amount 10 to 15% for validation. So we will just check whether it's giving you some result in the training. Is it what you want or no? So we can use post validation is a technique where the data is split into multiple subsets. So you'll just put it into small chunks. The model is trained on small faults and validate on the remaining one. So it will learn based on, and you will validate one by one. So repeating this process several times. So this is the type of validation. So you have plenty of validations that you can do it. You can set and test, split, hold out methods. Trend test, split, trend validation test, split. So you can just see based on. So we have k-fold methods, basic k-fold, trend series split. So you have plenty of these one, and you can see this one. So hold out is quick experiment, large data set, simple and fast. And its performance depends on one random split. So k-fold is more computation needed, and robust results uses data efficiently. So this is general use. So you have, if you have imbalanced classification problems, preserved class distribution, so you can use profile k-fold. So there are LOOCV, so leave out methods. So you have plenty of these validations that you can put on your training data, so that you should understand that there should not be any overfitting, and understand and your machine is learning it properly. So now comes overfitting. So you can see overfitting is just like this. It is just learning the same pattern as it is without any error or something. So it's just like overfitting occurs when a model learns the training model too well, capturing noise and details that do not generalize to the new data. So it does not know. So it's just like too complex a model, like too many parameters, insufficient training data. It can be the problems, too many features without proper feature selection, and also training for too many epochs in training data set. How it is, it's just like learning everything. Like if the dot is here, so it will also see, oh, this is it goes like this, it will go like this. So it's just like learning everything in the class without any update or something. Just you should learn. And when you put in the test, and there should be some question changed, a little bit change in your question if there is something new or something. So you will not answer it, because you just learned what was in the class, not from your side. So high accuracy on training data, but poor accuracy on test and validation test. So if your accuracy is good in the training, but it's very bad in your accuracy is bad in the testing and validation, it means that it is overfitting. And also large gap between training and validation performance. If there is, like, if your accuracy is like 90 and validation is 70, so it means that it's only learning, or it's only memorizing. So it's overfitted from yours. So it's not what you want. And then we have underfit, there is overfit, and there is underfit. So underfit happens when a model is too simple to capture the patterns in the data, leading to poor performance on the training and testing set. So in here, it is that you didn't study in the class, nor in the exam you did good. So it's just underfitting. You did in both area you failed. So it means that you didn't take part in the class too, and your exam is also not good. So in the training and testing, it's not giving you proper. So you can see this is my true values, but my prediction is this is my line. So this is the fit line. It means that it can understand in the training also, nor in the testing. So model is too simple. Using linear regression for the linear insufficient data training, it could be that insufficient training, too few epochs in the, we will see what is epochs in the deep learning, too much regularization, not enough relevant features. So low accuracy on both training and testing. If your training and testing, both of them are bad, it means it is underfit. Model fails to capture important patterns. So it didn't understand, this is my features, it didn't get any feature. So for this one, you can see a very good example is like overfitting is that whatever you are good at the class, but you fail in the exam, it is just like overfitting. But in underfitting is just like you fail in the class and also in exam. So it's just underfitting. So in training and testing, so both training and testing. But in here it is that it learns the training very good, well, but it fails when you are testing. So technique to reduce overfitting and underfitting is increased training data. More data helps the model learn general patterns instead of memorizing specific examples. So if the data is a lot, so it's very good for you and it's good for your algorithm. This improves the model's ability to generalize to new unseen data and reduce model complexity. Simpler models, fewer layers, fewer parameters are less likely to memorize noise in the data. This helps avoid overfitting, especially with the small data set. So you should not make too complicated, like using too many layers, too many parameters or something. It should be like you can have it simple if it is your small data set you have. For example, for this one, or our this model, like it's just one layer, it's one ReLU function, and it's giving you a perfect. But if you increase it, so it could be, you could make mess out of this. So it's up to you that how much data you have. And early stopping, so it monitor the validation cost during training. If there is something like the performance is less than 80% or something, so you can say that it should be early stop. When the validation loss starts increasing while training loss still decreases, stop training. Your validation is giving you 90, but your training is like 70, so it means it's increasing, so you can stop at that time. You don't need to train your model. Prevents the model from learning noise in the later epochs. So because if you learn more, it will give you worst result. You will just put early stop. Drop out from neurons, randomly turn off some neuron during the training, so you can just take out some neurons out of them randomly. Prevents the network from relying too heavy on specific models and force the model to learn robust and distributed presentations. So you can use these techniques for overfitting. So this is the model performed well on the test set, so it's a good model. If your model is doing very good in the test set, it means your model is good. But performed well on training set, it means it is overfitting. But if it didn't do in the training also, it is underfitting. So this is the complete diagram for your good model, that how it should be. So you are focusing on your test model, that it should give you a good answer in your test, perform good in your test. For example, in here, that's why we were using text test. It means we are testing our model. In here, we are training. In here, we are fitting, it's training. But in here, we are testing the loss. How much is the loss and what is the test accuracy? So and our loss is like this much. We are losing our data 0.08, but our accuracy is 97%. So it is in our test accuracy. We are not doing it on a training set. So it means that it should be here good, not in this portion. So do you have any question, guys?
No, sir. No question.
Okay. Only Mariam is here. Others, they are sleeping.
No, teacher, we are here. Just you are
Okay.
not here twice.
Okay, that's perfect. So I'm kidding. What happens during training? So we have forward pass. So you can see here, it is just the same. A forward pass is the expression, the process of sending input data through the network. So you are just doing from here, you are sending forward all the data. It computes the output using the network's weight and activation function. So as we are discussing, there is an output, there is a weight, and there is a bias. So it will always, and it will output will based on this one. So it will be here by here. So it will be just forward pass. Happens every time the model makes a prediction, both during training and implication. So you can see this is how it works. But we have backpropagation. It's also sometimes very good. So a backpropagation is the core algorithm for training neural networks. So you are training forward, it's going forward, then you are giving back also, just to check whether it's good or bad. So it fine-tunes the weights of the network based on the error from the previous epochs. So there is some problem in your this, so it will again go there, it will fix and come back. So by minimizing this error, the model becomes more accurate and generalized better. So there is a concept in mathematics, backpropagation. So this is based on that algorithm, backpropagation. If you have heard about this one, it's in mathematics. It's a very So it's here. So backpropagation is the core algorithm for training neural networks, efficient calculating how much network weights contribute to overall error. So you will check the overall error. So you will just, first of all, you will calculate this, then you will go back again to your, and see adjust of the weight through backpropagation. So you will adjust now your weights. The weights that you have, you are adjusting because there was some error. Based on that error, you are adjusting the weight so that there should not be any error. So it's a very good technique that you can use to better generalize yourself. So then we have loss function. So loss function is that how much this is how much difference they have. So loss measures how far the model's prediction is from the true level. It is a numerical value that presents the error. The goal of the training is to minimize this loss. So you can see here, we can see 0.088. So it means that it's very less. It means that our performance, our model is doing very good. So if you see the loss is 0.442 something. So it's very good. So for this, now for a loss function, we had for numbers, we have like mean absolute error. This one for images, we have some. So for this one, I have written here. That's good. So for this one is for our numerical. For numbers, mean squared error. If you have linear regression, if you have regression models, so you can use mean square model, cross entropy, and binary search. And so this one is for your regression. You can see here regression. And this one, if you are using classification, you are using for to understand or to get the loss, you'll use cross entropy. Entropy works with probability. So classification. If it is binary classification, you will use binary classification. It's one positive or negative. So you will write binary cross entropy. But if it is multi-class classification, you will use categorically cross entropy. If I'm not here, you can see categorically cross entropy. Spare category cross entropy because we had like from 0 to 9 digits. We were handwritten images, so we were using with many multiple. So we are using categorically cross entropies for loss function. This comes from here. This shows you how much loss you have based on this one. If it is binary, if it is like two images, positive, negative, so you'll use binary cross entropy. So you'll use binary cross entropy, and these all are the formulas. It's all mathematics behind this one. So you can use loss is equal to 1 minus 1 divided by n summation of this y, the true log of prediction plus y1 plus true value log of 1 minus predicted value. So this is how it works. So do you have any question with loss function?
No.
So this word was coming from here. So because we are using categorically cross because it was multi-class classification, so we were using category. So this is here. And then we have like gradient descent, which is like an optimization algorithm used to minimize the loss function. Think of it as a ball rolling down a hill to reach the lowest point. So if you are throwing a ball from here, so this is the minimum. So you will just take the minimum value for this one. So Each step, the algorithm moves in the direction of the step towards. So it is your alt, your previous, minus the n of the next one. So the hill is loss surface. So this is your loss surface. The ball is model parameters, the weights, and the slope is gradient direction, and bottom of the hill is minimum loss. So this is your minimum loss that you are having here. Then you have parameter tunings. So there is like parameters, you can see some layers you can tune. So parameters are setting chosen before training that controls how the model learns. So you are just trying to manipulate. So if you have n layers is 3, and the neurons is 512, and the learning rate is 0.1. You are doing it by yourself. So you are putting that it should be like this. It's all trial and error. It will give you 85% accuracy. But if you are learning, your layer is 3 and neurons are 1224, so it is 80%. And your learning rate is also 0.1. So it's up to you that you will just tune it yourself. So it's like hyperparameter tuning. So it's just based on trial and error case. So unlike weights, they are not learned by the network. They must be tuned manually or automatically. So manually is by yourself. Start by default is like if your learning rate L, this one is learning rate is L, R is 0.01. If you don't want to put it 0.01, you say that it should be 0.01 learning rate. And batch should be not, it should be 32 or 64, but you are trying to change it into maybe 128 or something. So use early stop to avoid overfitting with many epochs. Learn rate schedulers can help improve convenience. Grid search and random search can automate tuning. So I think I'm tired of reading, so you can read this later. So this is learning rate. So it's how they should learn. So the learning rate controls how a peak step gradient takes when updating value. So it's just that how much it should take. Is it like this much, small, or a lot? So it's up to you. So if it is too small, very small steps down to the slope, converts slowly and may get stuck. So it may get stuck, but it's doing here good. It's converging. Too large, it is failed to converge. This is too large. I think it's failing. And just try. So you will just try to do it yourself. So it's just trial and error. If it is too much, so you'll just try to make it less. If it is less, so you'll make it more. Update it weights accordingly. Then we have batch size. Number of training samples processed before the model updates its weight once. So this is instead of updating after every single example or after the entire data set, training makes in chunks. So you will just make this one into small chunks that it should be 128 small chunks, how much it should be. So you have a stochastic, mini bench, full bench. You can go and see the pros and cons. You can just go through these slides. Then we have these epochs. So one epoch is one full pass through the entire training data set. One training is that you go all your training. So it is one epoch. If you go here, like I used in here 5 epochs. It means it will go 5 times. It will learn your training data set 5 times. If you make it 10 epochs, it will take 10 cycles. It's up to you that how many cycles do you want to take based on this one. So if it is, so you can say one full pass through the entire training data set. During each epoch, the model performs forward pass, makes prediction, compute loss, runs back propagation, updates weight. So you can see here, it will just give you from each time when I'm having 5, it will give you the loss function and the accuracy. So by this, you can understand that how is my training doing? Is it good or not? So at first my loss was high, but in the second it got less. The third it got much better. It got better. And also the accuracy in the first it was 87%, then it went to 96, 97, 98, 98. So you can see here this is in each when you are completing one cycle on your training set. So it's called epoch. So do you have any question, guys, so far?
Yeah. No, sir.
Okay. Then we have optimization, like we were having ADAM or SGD. So full name is stochastic gradient descent and adaptive movement estimation. So it updates weight using gradient on current page only. If you use this one, so it will update your weights, uses momentum adaptive learning rates for each parameters. So it's simple, memory, effective, and good generalization. But the cons is that slower conversions, sensitive to learning weights. And use case is baseline training and small data set. For the small data set, you can use stochastic gradient descent. But for deep learning, you can use Adam. So can overfit if not tuned slightly more memory use. So you can have optimization. In here also, if you are using Adam, so this is an optimizer. You can see here, this is optimizer. So you will use, while you are compiling everything, so you will have to use this optimizer of Adam. And this is metric is accuracy, so you're just getting accuracy here. This is all that you are doing it while training. So why AI ethics matters? Ethics are principles and practices ensuring AI technologies are developed and used responsibly. Like it's something as always everyone knows: fairness, transparency, accountability, privacy, and safety. So ethical AI helps build public trust, avoid legal and social consequences. If your model is, if you are doing a model on the wrong data set and the people are using, so they might take you to court because could cause legal issues for you because you are playing with someone's life or some problem. So someone can come to you and say that your training is not good or fine. So there could be an issue and social consequences. So ensure inclusiveness in your while you are using AI. So biases and discriminations, privacy violations, lack of transparency, and accountability gaps. So model learns and amplifies human biases. So you can see all of them, these issues. So thank you for your class. Do you have any, oh, do you have any question, guys?
No, teacher.
That's perfect. So if for 5 minutes we have one of our students from University of Central Asia, Asma is here. Asma, can you hear us?
Yes, I can hear. Can you hear me?
Yeah, so this is how you can like how they are doing these things in their university. For example, in the University of Central Asia, so they are using some tricks, tools. You can also use these tricks and tools, which Asma will show you. Asma, the floor is yours. You can show how you are doing it presentations in.
Okay. So, hello everyone. I hope you're doing well. I'm Asma Al-Saini, computer science student at UCA. Maybe some of you know me during the application forms and this stuff. So your instructor just asked me to show you how to have a dashboard and with the Streamlit. You can use any tool for having a dashboard, but one that I will show you today is the Streamlit. Like it's one open source Python framework that you can use because you're working with the Python. So I will share with you and I'll show you like just a minute.
You can share your screen. We don't have your screen.
Yeah, I can share. Yeah. Can you see my screen now?
Yeah, yeah.
Good. So I'll show you this dashboard that I had for one of my projects for the image processing. You can have just a Python file. It's in my download. So I will go from here, from any directory that you just open your CMD. And it's very simple. You just write Streamlit.
Streamlit wrong.
Streamlit.
The spelling is wrong, Streamlit.
Oh, sorry.
Because it will give you error.
Yeah, Streamlit run, and the name of your file. I think it was, and don't forget the .py, and you run this command. Oh, sorry.
No, dashboard is H is missing.
Oh, okay. And here you can see I have a complete dashboard for everything. I have different sections for digital image processing, for design and analysis of algorithm, for optimization, for everything. So if I go through image processing, here you can see it asks me for an image. I'll just real quickly. So here for every part, I have different sections for enhancement, contrast, resizing, or segmentation, and again, so many other sections, which one I want to use for noise and this stuff, binarization or grayscale. It will change and it will give me, and or even resizing, or even contrast. I can have a histogram equalization. I'm not sure how much you're familiar with image processing, but you have these parts like it was in our course, and we had to implement all of them. Or for design and analysis of algorithm. Oh, sorry, I have some problem here, but it's like it shows me monster theorem, iteration methods, fraction, or even coin changing, Huffman problem. It all works, and it shows you encode. You can encode and decode the text, and for optimization. So it's like just simply you can have your dashboard with Streamlit. It's very simple. You just open a Python file, you write your code there. Even if I show you the code, here you can have all your codes just in one page, and it easily make you a dashboard. Yes.
So the same as Asma mentioned, so you can see the import. You will just import math, random, whatsoever you are doing there. You will just do it here on here. But it should be the one thing that it should be .py format, because the other format it will not work. It should be all in this. It should be in one go. It should not be, there should not be any like .ipnb or some other files, but it should be .py. And you can see how these all things are happening perfectly for. Thank you, Asma, for your.
You're welcome. Thank you. Have a good day.
You too. So this is like you can do it like now you can use modern tools like maybe Streamlit or other for your making dashboards, which is very easy to do. Like you will just find out what is your need. So then you can use your images, your graphs. You can make graphs on this one, that how it was. The one that I was showing you and it was deployed for my final year was also like in Streamlit, and it was deployed. So you can find it into internet, even the website, everything. So this is how you can do it. Do you have any question, guys?
No, sir.
Okay. If you don't have any question, then see you on Wednesday.
Thank you, sir. See you on Wednesday. Have a nice
Thank
day.
you. You too.